Namaskaram. Today I will penetrate into the topology of the earth, the size of the earth, the shape of the earth, and its history. So we begin with our ancient stalwarts, including Pythagoras. Pythagoras was the first to give an estimation, if we say, of the Greek era, not including the Indian version. If we say of the Greek era, Pythagoras considered that the earth might be something of a sphere. Why he considered this? For him, it looked as the most perfect geometrical shape. A circle in 2 dimensions or a sphere in 3 dimensions. These are what he considered. There were many shapes which were discovered by his school students, including the dodecahedron. So out of all of this, the sphere had the most symmetry, and he could understand that and proposed it. But this was something of ad hoc hypothesis. Pursuing the matter, Aristotle claimed that the earth should be a sphere on other basis. One basis was, if it was a sphere, then if there was something of light rays coming out of the sun, then some of the rays would penetrate and some of the rays would be blocked by the earth, and due to such a phenomenon there would be an eclipse, and thus the nature of the eclipse that we see right from here is that the moon is covered entirely or partially by the earth, but in such a way that it shows the structure of the earth must have been something like spherical in order to have such a display of dark light, isn't it? So this is one of the partial eclipses. There were several eclipses, but all of those entails that the earth should be spherical. So these are two of the phenomena. It could be rather to say hypothesis as proposed by Aristotle in favor of the argument that the earth was spherical. But the real credit that the earth was spherical goes back to 200 BC to the head librarian of the Alexandria library, and he was named Erastosthenes. You must have heard him in prime number theory, the sieve of Erastosthenes. 1 to 100 we write and we cut out the multiples of the prime numbers, and in this way we can sieve out what are the other prime numbers, isn't it? There are many ways of doing it. For example, for 1 to 100 you have to do it up to root 100, that means up to 10. For 1 to 1000 we have to do it up to root 1000, and you can sieve out all the prime numbers. So we will not go deep into this. We will rather be lateral, and will be attentive towards what he said about the structure of the earth. So he too believed, the Erastosthenes too believed that the earth was round. Now what he had known, he knew that there was a he was posted at Alexandria. First we write that. And there was a city called Shin. Shosyn. There is another name to it. I've forgotten it. Sweetheart or something like that. Shin. Okay. The Shin was lying on the Tropic of Cancer, and Alexandria was down. Alexandria was a little down. So who forbids us to make the visualization? Okay. Very good. We are not so good at drawing circles. I have seen on YouTube many people who comes and just revolves the whiteboard pen and it is a circle. I will practice it, but now with chalk. Okay, now he considered Shin to be located somewhere like that. Let Shin be denoted by S, and Alexandria a little down. Okay, now whatever he saw was on 21st of June. What do you call it? Summer solstice, isn't it? On 21st of June, a stick which you land at Shin throws no shadows. The origin of the phenomenon is from the ancient knowledge that the great whale of Shin, there was a great whale of Shin, casted no shadows on 21st of June, 12 o'clock. 21st of June, 12 o'clock. Isn't it? It casted no shadows. That means there was a well which was in Shin and it casted no shadows. That means you could see deep down the well on this day, on 21st of June. So this is a remarkable observation. How remarkable? For it was termed remarkable by Erastosthenes. He then placed the stick at a position in Shin and found no shadows. Okay, found no shadows. So if there is no shadow right here, that means light was coming perpendicular to the flat surface here and parallel to the stick. Okay, so light was coming in this manner. As the earth is much away from the sun, the light it receives is almost parallel at every point. That means either we take a north pole or a south pole, it doesn't matter, light always comes in the direction of light, just from the sun. So in Alexandria also too, it must come in this manner, isn't it? Now we take a insight, and in Alexandria we take the stick a little more extrapolate it and see that there must be a shadow which is thrown by the sunlight for the stick that is embedded perpendicular to the surface at Alexandria. So measuring this part of the shadow and the length of the stick, one could measure tan theta if this is taken as theta, tan theta. So one can measure theta, and this is the almost end of the argument. For the rest of this is triviality. So how triviality? We will go into the triviality. See, we'll extend this portion. This we know that this is perpendicular, stick is perpendicular to the surface, and if we extrapolate the stick, then we'll always go through the center, isn't it? Now now we'll have some other calculations. Now we'll take the stick that is at sheen and similarly extrapolate it, and these two will go through the center. So this is the center of the diagram, isn't it? Okay, now see here, this thing is parallel to the sun rays, and this thing is just the sun rays. So sun rays and sun rays are parallel, and we have an intercept here. So these are alternate interior angles, this and this and this. Okay, so this is equals to theta also. This is also equals to theta. So it was known that after measurements that Erastosthenes calculated that theta equals 7.2 degrees. 7.2 degrees. Okay, we know theta equals 7.2 degrees. Then theta equals 7.2 degrees. Now there is a crucial step which we left here. Mr. Erastosthenes calculated also the distance between Sheen and Alexandria, and it is absolutely required, at least in this problem, to calculate the perimeter of the earth. So what he did, he hired men who were pedestrians and who were expert workers, and worked in almost equal steps and calculated the distance between Alexandria and Sheen, and it was calculated to be 5,000 stadia. 5,000 stadia. Distance between Alexander and Sheen was calculated to be 5,000 stadia. Then 5,000 stadia, or I think 2,000 kilometers. Yes, stadia gives you 5,000 stadia gives you 5,000 stadia is something which, this is 5,000 stadia, it subtends an angle theta, and what is the angle? 7.2 degree. Okay, we are right in the track. So 5,000 stadia. Now we want what will be the entire thing, entire arc, or the entire curved line that will subtend an angle 360 degree at the center, and that will be the perimeter of the earth, and that is all to it. So 1 degree is subtended by 5,000 by 7.2 stadia. 1 degree is 5,000 by 7.2 stadia. This is unitary method, nothing more than that. Then 360 degree, this is the value we want to calculate, and this gives us 5000 by 7.2 into 360 stadia. We take 5000 stadia to be equal to 2000 kilometers, and the result comes out to be equal to, I will write this in kilometers, 40,000 kilometers. See, this is not something esoteric, isn't it? Everyone can follow it. So, and the modern calculations, see how it matches, how much it matches, so well it matches, it almost catches up with the modern non-terrestrial value. I think it is 4030 kilometers. This is how Erastosthenes in that age calculated the radius or the perimeter of the earth. And later there was someone called Shirin who used an astronomical observation to calculate the perimeter of the earth, and it came out to be extremely less than the part calculated by Mr. Erastosthenes, and the later calculation, which was much less, I think triggered many earth travelers, including Columbus and Amerigo Vespucci, to travel across the world. If they would have known that the world is 40,000 kilometers long, they must not have been much clear about their voyages. And that is all for the day, and next day we'll speak about some other heavenly bodies, but till then, stay tuned.